pose your questions, and engage in a meaningful dialogue with the speaker. Feel free to participate actively. Thank you.
Thank you, sir, for a welcome note. Now, I would like to invite Dr. Ramisha TV, Junior Scientist, Water Transportation Division, NATPAC, to introduce the speaker to audience.
Good afternoon, all. Today we have Dr. Aitichya Chandra, presently working as a research associate in Resilient Network Asset Management Group at the Department of Engineering, University of Cambridge. Dr. Chandra's work focuses on developing techniques and algorithms to model the operation and dynamic behavior of networks with an aim to develop optimal policies for improving network resilience. Dr. Chandra completed his PhD in Transportation Systems Engineering from the Indian Institute of Technology, Indian Institute of Science, Bangalore in 2024. His PhD focused on developing novel air traffic management solutions for gate-to-gate aircraft operations. His overall research interest lies in network modeling, transportation system, statistical modeling, and optimization. During his PhD, he was awarded the Prime Minister's Research Fellowship from 2020 to 2023 by the Government of India. With this note, I welcome Dr. Aitichya Chandra to this talk series. Thank you.
Thank you, ma'am. Thank you, sir, for inviting me to this very interesting and very engaging Transpedia Talk series. Hello, everyone. Good afternoon. It's a delight to be a part of this esteemed list of speakers who have been a part of this series. So I'll just briefly discuss a couple of chapters which are an integral part of my overall PhD thesis, and today's talk is titled on modeling an efficient system for airport arrivals and departures. And as we move forward, I would like to give a very concise intro of where this airport arrivals and departure systems kicks in. Please feel free to drop a question in between and interrupt it. It's absolutely fine. Now, when we all have used the air transport system as a very critical mode, especially for long distance travel, and without a doubt, we have seen how the airports and the airport infrastructure and the airport connectivity, the aviation connectivity in India, in the Indian subcontinent and around the world have consistently increased to a point where we have almost become very, very dependent on aviation as a mode of transport. Now, if in a nutshell, if I capture the journey of a flight, we start from the gates. That's where the aircraft starts its pushback, goes to the taxiway, goes to the runway, and then takes off. Then there's something called the approach departure, where it goes to the top of the climb, and then it follows the en route sector or the en route routes. And then just when there's an approach and arrival at an airport, it starts its descent. And this is where many of the pilots might announce that, ladies and gentlemen, we are about to start our descent journey. It follows the approach arrival phases, and there are different rules here applicable just to ensure the safe and ordered arrival of traffic. Arrival can become a bit tricky than departures, and then finally it lands and goes to respective gates. With that in mind, let's see how how the situation comes and how operationally it comes into picture. You can see that aircraft, when there's a high traffic, they are lining just before takeoff. You can see it in Mumbai, you can see it in Bangalore, all the major airports around the world, and in some cases, even in arrivals as well, there's a line of the complete list of aircraft that are about to arrive at a given airport, right? And in general, there's a huge amount of traffic at any given point of time. I mean, roughly, if I quote the correct facts, maybe it's somewhere around 30,000 to 35,000 flights that are on air at any given point of time around the world. The question is, how is this traffic managed safely on a day-to-day basis? Because even before we develop the model, we have to understand these operational intricacies of their management. This is how a typical air traffic control structure works. You have the terminal control and the aerodrome control, which is around the airport, and you have the oceanic control, right? So the and there's a transition zone between the airport and terminal area control and the oceanic control, right? It is this transition zone that kind of poses a very difficult region or difficult situation for the air traffic controllers. Most importantly, because it exhibits a continuous dynamic interaction of converging and diverging 3D traffic. So traffic is not just 2D here. You have converging aircraft when they are arriving. You have diverging aircraft when they are departing. Sometimes the converging trajectories and the diverging trajectories have complex interactions, and they do it in a three-dimensional manner. This is how the hierarchy and the chain of responsibilities gets forwarded. So the moment an aircraft is on the ground at an airport, it is handled by the air traffic control. Along the approach phase, either departure or arrival, it is handled by the terminal radar control, also called TRACON, or sometimes it's also called TMA. Then it goes on to the en route controller, who handles all the en route traffic. And finally, the moment it starts its descent, it goes back to the arrival controller, which is again the terminal radar controller at the arrival airport. Right. So this is how this chain of responsibilities shift between one controller to another controller and to another controller. Whenever you are flying, you're always in very safe, skilled hands who make sure that there's enough separation between flights, and all flights adhere to all safety norms. So these controllers are kind of the foundational block for the overall air traffic management around the world, not just in India, everywhere. They follow the same rule, they follow the same procedures accordingly. Now, let's focus on terminal maneuvering areas, or TMA, right? Because our idea is that because this TMA represents the transition zone, and it has a complex traffic. Let's dive deep into it. Into the TMA, if we look into the overall structure, what will you see is that you have kind of, as I said, a converging trajectory following through the guide path that represents the landing segment. And you have flights that are ascending at these and follow these glide paths to the runway. And similarly, there are out paths, which again, the flight has to follow. This terminal area serves as a very important bottleneck because of the high volume of traffic and the complex environment that I just mentioned, right? If I look closely into the arrival process, the whole arrival management process starts somewhere on the extended TMA, which is called the ETMA. And these represent the entry fixed points. That's when the descent starts. And after it enters the ETMA, the controller radar detects it and assigns some approach path, and then it starts its initial approach segment. There's something called the mid descent phase, which starts after approach segment, and there is something on the final approach segment, which is near the runway threshold. This is the last point of decision. If there are turbulent winds or side winds and things become critical, this is the last point of approach before which the pilot has to decide, should I land or not? And this is what I mentioned about the missed approach point in the final approach segment. So at this point of time, the pilot has to decide, do I want to land? And if the environment is not sufficient enough or not feasible enough for the flight to land, the pilot might decide to just take off, right? Departure process is, again, you have a converging geometry in arrival. On the flip side, just like a symmetric phase, you have a diverging geometry in departure, right? So you start with the pushback, it goes to the taxiway, and then it goes to the runway threshold. It starts the departure segment and then climb to the en route. So it's the same thing again and again. This is just to give a brief detail about how this happens. Now, there are also separation protocols in practice, and these separation protocols are very much like, it's very much a heterogeneous function of the type of aircraft. If you have, let's say, two large body aircraft, they have to be separated by 4 miles. you can follow a medium body aircraft after a heavy aircraft, and they can be separated by a mile or 2 miles, something like that. So the separation between two flights is a function of which flight is the leader and which flight is the follower. And this separation is mainly ensured both during arrivals and departures, is to avoid something called the wake vortex separation. So we know that flights run on turbines, right? And they have their own propulsion. So when a flight takes off, or whenever a flight is at any phase, either on ground or in air, it creates a pressure differential after it. And because of that pressure differential, if we do not give sufficient time to so that the pressure differential goes away, and if another flight occupies the same position, it might not get enough lift to continue flying. And that's why these safety protocols are mandated all across the world consistently. So in a nutshell, this whole arrival and departure are roughly summarized into something called the standard instrument departure procedures and the standard terminal arrival route procedure. So this is called SID procedures and STAR procedure. The SID and STAR procedure gives the exact path, exact heading angle in which the flight is supposed to depart or supposed to land. It also gives at what waypoint in the path they should follow certain given speed restrictions. So these are fairly regulated procedures all across major airports. And you can see just an example. I've given a STAR procedure for Delhi airport, where let's say they're supposed to land on runway 29 and they are coming from somewhere which connects to route 218. They have to follow these waypoints and these angles and these speed limits. Similarly, I've given a SID procedure for Delhi, which is a departure procedure. And let's say they are, again, taking off from runway 29, and they are supposed to go around this route of W19 and Q23. They have to follow these angles, these waypoints, and these speed restrictions. So these are fairly regulated, right? If I can capture that in a much more inclusive geometry, and a much more simplified geometry, then this is how it looks. This is the STAR procedure. You have, as I said, you can see there's a converging geometry here, and the SID procedure, which has a diverging geometry, right? Something to be noted that there are holding areas in the arrival in the STAR procedure. These holding areas are essentially to provide some cushion to the arrival aircraft if they are getting delayed or if there's a congestion at the arrival airport. For departures, it's fairly simple. You can hold them on the ground. You can hold them on the gate. You can hold them on the taxiway or just before they enter the runway. And if there's any congestion, if there are any challenges in the takeoff. But for arrivals, the flight is already on air. So you can't really do much about it. What they do is that they sometimes go into the holding pattern, which means they have a fairly designated regions, and they are supposed to circle this region and unless a traffic controller tells them you're okay for the landing. So this is where you might feel, there are sometimes when the pilot has already told that we might land in 20 minutes, 25 minutes, but there's still some delay, and it might be because there's a congestion at the arrival airport, and it might, then the delay is how the pilot is managing the delay is they're going into the holding pattern. So it's an interesting procedure just to absorb the delay during the arrivals. Right now, this is how the geometry of it, the operational structure of it. How do you manage them? How do you manage them? Generally, we go for operations modeling approaches, right? Technically, if I can briefly categorize the modeling approaches, they are in 4 different categories: the routing, the runway allocation, the sequencing and scheduling, and trajectory optimization. For arrivals, routing is choosing which STAR route am I supposed to take. For departure, which SID route am I supposed to take? And there are some factors that affect it, and it has its own complexity. There's the runway allocation, which means which runway I should take off from, which runway I should land, and of course, there are other different factors that takes care of it. Also, the third phase is about sequencing and scheduling, which means that in which order. So if I am supposed to take, if I have flight 1 to 10, ready for takeoff, what is the sequence in that flight 1 to 10 should actually take off depending upon their expected time of departure and all other factors. Similarly for arrivals as well. There might be 10 flights about to arrive at Chennai airport, and there might be some situation where when one flight needs to arrive early, there might be some emergency, there might be some cases, and then you have to reshuffle the whole schedule. So it's a purely it's a very dynamic decision paradigm, and it's a very interesting problem to deal with. And then comes the trajectory optimization part. It is that you remember that I talked about the glide path and the path that an aircraft has to follow. In most cases, this is not the job of the controller. It is the job of the airline and through pilots to follow those descent and climb profile trajectories. And sometimes it needs medium precision. So as I said, the three phases that are marked in this shape are the controller's responsibility, and the trajectory optimization is an airline's responsibility. My focus, or I thought that what the world is focusing on is more how to minimize controllers' workload, and to achieve that, we need to address these three phases. Now, so this is the synergy. So we have routing, we have runway allocation problem, and we have the sequencing and scheduling problem. Each have its own objective, right? And each have its own goal, and each have its own advantages of achieving that. There are some popular tools that are already being used at the major airports. There's something called the Airport Collaborative Decision Making, or the ACDM. What it is essentially, it's a very comprehensive data aggregation tool where you can see the status of each and every aircraft that are either on ground in the airport or near the aerodrome area or within the terminal area. And you can keep an update of every possible time shift that is happening to each of the aircraft. And this ACDM is being used very robustly in an airport like Mumbai. It's being used extensively in many European airports as well. There's something called the Arrival and Departure Manager. Again, it's a decision-making tool where you have arrivals and departures lined up, and then the controller can decide which sequence to allot to, or if the controller wants some suggestion, there might be a lot of flights that are arriving very closely to each other. For example, you can see there are almost 4 flights landing at 1 or 2 minutes of interval. In those cases, if the controller can't really decide on their own, they sometimes resort to this arrival and departure managers that will help them make decisions. So a question naturally arises that if everything is already there, then what is the point of academic research, right? All these tools are there, all these softwares are there. There's not much should we do about something about it? Reason is, even though these tools are there, we have seen a consistent increase in flight delays. And these increase in flight delays is because of an increased congestion, humongous growth in air traffic, and of course, all airports are limited by infrastructure, their restrictions, right? We cannot just make more runways. It takes a lot of space. It takes a lot of resources. Passengers have become more sensitive to their comfort and delay, and there's control because of the workload. Sometimes controllers get a lot of fatigue because it's a very high stress job. The weather conditions due to climate change have become worse, and there are so many different arrays of problems that we are facing right now, and simply infrastructure augmentation might not be the ideal solution everywhere. And of course, it's definitely not an ideal solution in terms of the cost resources involved. And the tools that we have are as good as the models inside them, right? So this is where we have the idea that can we improve the model, right? Now, what I'm going to propose are 2 new modeling strategies, right? The arrival management model and the departure management model. Now, remember, this is just reiterating the fact that we had the routing problem, we had the runway allocation problem, and we have the sequencing and scheduling problem. Our focus lies somewhere here. how to cater all these three phases to make sure the workload of the controller is as minimum as possible and they can manage the arrivals and departure very, very safely. Now, if I think of this zone of interest, and let's look them objectively at each of the individual problems. If you see that, it means that there are individual problems itself are quite complex. And if I combine them together, if I want to address them together, what we mean is that we have more decisions, we have more constraints, and we have more uncertainties. Each problem in itself can be a combinatorial problem, and we know how tricky combinatorial problems are. If we add more complexity, it's just going to have a combinatorial explosion, and it becomes very, very difficult to solve. Okay. So can we do something to decrease the complexity? That's where I made few assumptions. For example, I said that if I can capture the star and SID track time, then I can capture the routing complexity and the routing path patterns or the path deviations. If there is single runway and we have efficient operation, then a single runway itself can manage an increasing amount of traffic as long as we do the scheduling in a very efficient way and we take care of the conflict and safety separation altogether. Now, these are not just any random assumptions. We have established these assumptions through 3 different papers. We have validated these assumptions, and these assumptions holds true. Given these assumptions are true, how do we proceed, right? For example, and this is where the modeling starts. So for first step, we need to take care of the safety separation and the star and SID path or routing effects. I might use path and routing interchangeably. I'm sorry if it become confusing at times, but yeah, I'll use path and routes interchangeably because kind of sometimes they mean the same thing. So let's think about during arrivals and during departures. Let's say in arrivals, you have the flights that are coming from the start transition points and about to arrive at the runway. And let's say they have the designated time at each of the arrival waypoints, and they have to satisfy a minimum separation between them, right? The idea is that you take into effect the star and SID routing effects, star and SID routing variations. You plug in those variations in the time they are showing at each of these phases, and then you add the minimum separation constraint between them. Similar thing for departures as well. You have flights and they are departing, and you plug in the effect of SID, the SID routing complexity. You plug in those complexity into the time calculations, and then you add a constraint that ensures that there's a minimum separation between any 2 departures. Right. There's also a sequencing constraint. It means that what should I decide? Should, let's say 2 flights are there in the air and about to approach an airport. Should flight 1 land before 2, or should 2 land before 1? And that will add a bit of mathematical notations into the model. Similarly, for departures, we have to think, oh, should flight 1 leave before 2, or should it be other way around, right? And at any point of time, only 1 can be active. Either 1 can leave before 2, or 2 can leave before 1. There cannot be a misjunction between these 2 agreements. Let's think about another constraint that we have to add while modeling. Let's say while the flights are arriving, remember we talked about holding, right? They can hold, but not beyond a given maximum holding time, right? Nobody like delays, but there might be cases where I cannot achieve the safety separation. I cannot achieve, due to the routing complexity, due to the star and SID route complexity, I cannot achieve the desired time. Okay, fine, let's delay it, but how much? So we have used, based on literature, we have found out a particular holding time windows. So let's say a flight cannot be delayed by more than 15 minutes or 25 minutes. So that's when the scheduling kind of shifts the flight a bit so that you accommodate every flight as much as possible. Similarly, for departures as well, you have a maximum holding time at ground. Now, both these time window restrictions for arrivals and departure it tries to follow the window between the target landing time or target departure time and the latest landing time or the latest departure time. Finally, conflicts, right? Remember, these are, as I said, there might be some cases when there might be some conflicts due to delay or the path they are following. Turns out there were no equations that can connect conflict due to arrival and departure delay in the TMS, SID, and STAR. And that's where we thought maybe it's better to develop a new delay conflict relationship. So we thought if we can model the probability of conflict as a function of delay, but that would be a very parsimonious, it's a very small model. You cannot, fit a lot of observations in it. So we thought, can we add a bit more extra variable into it? Remember, when we are discussing all these things, we were consistently talking about the path, the waypoints that are being followed, and how the flight has to adhere to the restrictions on all those waypoints. So if I can just use the number of waypoints that a flight is traveling during both arrivals or departure, then those waypoints kind of reflects the operational variability there. And that's where we thought, let's model the probability of conflict as a function of delay and the waypoints crossed or about to be crossed by the flight. And this is where we assumed a logistic function between them. And that led to a delay conflict relationship at a merging point. So this is the final equation where the probability of conflict follows an expression, which is a function of the delay at a given point and the waypoints that the flight has crossed since the delay point. The advantage of this equation is that it's a closed form equation. Beta naught, beta 1, beta 2 are fairly data-driven estimates. So you can adapt it to any given airspace and airport if you have the relevant data. So and based on different sensitivity tests, we found out that let's keep the probability of conflict at 0.45 because that gave the highest accuracy when we compared the predicted probability of conflict from the model with the actual probability of conflict that was happening at air. Now, remember, the geometry is very different. So earlier, the safety separation, the sequencing constraint and the time window were fairly similar in terms of the equations that I wanted to implement. But because the geometry is different for arrival and departure, I cannot use the conflict equation as it is. So for arrivals, let's say we have the objective of minimizing the delay. For departure, we also have the objective of minimizing the delay from the expected departure time. Same goes for arrival from expected arrival time. Star has merging conflict, so we can put the number of conflict as an upper bound. So let's say we do not want more than 4 or 5 conflicts because beyond that the controller workload becomes significant. From the delay conflict relationship, the expression we got, and we are assuming a binomial distribution, we can get a very nice tractable function of the number of conflict, and then we can put an upper bound on it. So this delay conflict relationship becomes a constraint in our arrival model. In case of departure, we do not have merging conflict, because there's a diverging geometry. So we can think of having a preemptive consideration of the on-route conflict that might happen due to departure delay. And for that, we revise the objective function to minimize the conflict arising from departure delay, right? And this is how the final objective function looks like. We implemented the model. The results are already published in 2 separate journal papers. For the data that we used to implement the model, we used the Chennai data. Why? Because we had collaborations with Chennai Airport Authority of India, and that's where I was getting the data from. So it was really easy. But the other cases also, Chennai represents a typical congested airport. It has handles almost 22 million passengers and 178,000 aircrafts every year, and it's technically the 4th busiest airport in India. And this is how the SID layout in the most simplest form look like, and the star layout in this most simplest form look like. We also followed a dynamic implementation. Remember, we are talking about a dynamic environment, right? These models are static. Of course, when we talk about the SID and star time routing complexity, we are taking non-deterministic time functions, which means that they are not deterministic. They are not static values. We have to draw them from a distribution. But what about time? Remember, because let's say I can fix a schedule for the next 40 minutes based on the arrivals that are happening in the next 40 minutes, but something just might change, and then I have to reshuffle everything. That's where we followed a rolling horizon approach. So in the rolling horizon approach, we have something called the freeze horizon and the scheduling horizon, and the total duration is called the planning horizon. So let's say in my planning horizon is from 5 a.m. to 5:45 a.m. I'll take all the flights that are expected to arrive or depart in this window. I'll run the model, get the results, and freeze the first 15 minutes. That's the freeze horizon. Then I'll use the results that I got from the first iteration and I'll add the next 15 minutes. So now my planning horizon starts from 5:15 to 6. And the schedule in this window is actually a result of the last model run. And in so on and so forth, we continuously update our model iterations so that we can take care of any uncertainty or any change in weather, any change in timing, schedules, and emergency into the planning horizon. So we only freeze 15 minutes because that's the minimum time that a flight should be given or a controller should be given to take decisions. But we run it collectively over time so that any kind of dynamic uncertainty that can happen further in time gets accommodated, right? And these are some of the key results. I mean, I'll of course say that the models worked and everything, so I won't want to put much time in discussing the results, but just in a nutshell, we were able to obtain optimal sequence with minimal delays, and the scheduling actually reflected the congestion behavior. So at times when the congestion was high, the scheduling had a higher average delay, and at times when the congestion was very less, the scheduling made sure the flights are just on time, like every time on time. The scheduling was also a representative of the airport traffic, the sit and the start geometry, and the routing complexity in the TMA. We also validated how the model, the throughput, or the let's say the throughput I got from our model sequence and schedule matched with the observed throughput, and there were no loss. Essentially, sometimes we are doing better. And in a nutshell, if you can say, is that we had nicer capabilities or more comprehensive addition of some interesting uncertainties without any loss of runway throughput, and that was fairly encouraging. If we compare the model implications, so the airport arrival management model, it considered the merging conflict. It has the propensity to reduce task complexity and in turn the controller workload. The departure management used the new delay conflict relationship, and it considers the preemptive conflict workload that can happen en route at the airport level itself. It also took care of the SID and taxi geometry. These are some other non-trivialities that I have not explained in this one, because I did not want to be a very mathematical talk in that case. But yeah, we have taken care of every possible effect that can happen due to taxiing or due to geometry as well. These are some more interesting implications. The model closely adheres to the first come first served logic, which means that unless there's no emergency, we'll try to make sure the flights arrive and depart in the time sequence they are scheduled to arrive and depart. And given the time window restrictions, we have implicitly considered passenger comfort and fairness and equity. And this fairness and equity actually leads to higher acceptance by the airlines of the schedule. So sometimes, and we have been in workshops where the airlines complain that the controller might prefer some airlines over another, and they will give them a quicker arrival time or quicker departure time, but that's so not the case. The controller do not really have any bias, in most cases have any bias against any airlines, and just to remove the bias and improve the acceptability of the model results to the airlines, this model have kept it fair and equitable. Finally, these models are fairly flexible and adaptable. The constraint that we discussed, the geometry that we discussed, exists all around at every airport around the world, and it's this flexibility and adaptability that actually enhances its integration to existing solution tools. So the existing tools like Arrival Manager, which is called AMAN for arrivals, or the flight arrival and departure system. And similarly for the DMAN, which is a departure manager, they are kind of built on the same principles, operational principles that have been followed by the model that we proposed. And in that way, we ensure that these, if we can just translate the model through code and integrate in the existing system, they should be able to work, and they should be able to work with the exact data that the systems take input from the airports. We have also extended the models to multiple runway configuration. So remember, we talked about the runway assignment problem. So if there are multiple runways, we have shown the results that we extended the model to show that we can also choose which runway at what point of time. Yeah. So that's it from my PhD work perspective. It's interesting to understand, what does the future hold for us. Now, what I see, like, just again, so this is completely my experience, is that we are looking forward to either more tractable modeling approaches or fast solution approaches, or somewhere a hybrid in between them. Now, remember, these problems are quite complex, right? If even the most simplest scheduling problem can have a complexity of OP to the power 3, if we allow more and more uncertainties and more and more constraint, it becomes almost intractable and very, very hard to solve. So the idea is that we can move to more tractable modeling approaches, which kind of incorporate digital twins or simulation-based approaches, or something like probabilistic graphical models, game theoretic models, or agent-based modeling platforms. These paradigms allow more adaptive and more scalable tool to handle a problem of this nature, so you don't have to always resort to mathematical models. We, at the same time, if we are resorting to mathematical models, we have to look for faster solution approaches, and they can either be on these well-explored paradigms of column generation, branch and price method, because these models are mostly mixed integer programming models, or they can go for the more very popular approximate methods like heuristics, meta heuristics, and sometimes a mix of heuristic and meta heuristic, right? So yeah, either we go for tractable models or we go for fast solutions, because remember, we are working in a dynamic setup. We need fast solutions, fast and optimal solutions. So either you enhance the model, or you enhance the way you solve the model, or you put them together. And last, and something, this is again just something that I'm interested in, I'm working as a part of it, is the reinforcement learning paradigm, where we have an environment. Let's say the environment is the arrival and departure operations. We have some state that reflects how the environment is working, and there's an intelligent agent that takes an action, let's say shuffle flight 1 and 2, and then see how much reward it can get. Let's say reward can be the decrease in delay. And then we go through all the possible combinations, and the agent learns what is the best action, so what is the best schedule in turn. And I think, again, this is just in theory. It's still not being implemented. We can even extend the reinforcement learning paradigm to something called the quantum reinforcement learning paradigm, because we have, if you have such a complex space where you have 50 flights, you can just imagine how many different combinations it can happen, and given you add more weather restrictions, path constraint, and everything, we need, and to attain a faster solution, even for reinforcement learning, might be a bit tricky. So that's where, given the advancements of quantum computing that we are having, we can translate, or we can break down the state and reward and the action interactions, and use quantum computation to get faster results. Note, the quantum reinforcement learning can, best cases, it essentially it minimizes the time, and instead of the reinforcement learning tries to explore everything, what QRL will do is that it will only explore the right feasible space, right? And this is an interesting theory, and it's something I'm working on the side, and I just wanted to share with everyone. Yeah, so that's all from my side. I really want to thank NATPAC for giving me this, for inviting me to this series, and yeah, it was a brilliant thing. That's something, so on a lighter note, just to leave the audience with something like that, I think this is how most academic research works. Ideally, you should work when you have more stuff, but I don't think it works that way. The more we have, the more we procrastinate. And yeah, that's it. Thank you.
Thank you, sir, for the enlightening presentation. Your insights were invaluable. Now the forum is open for discussion.
Hello, this is Anish. It was a good presentation.
Thank
Thank
you.
you for sharing it. I just had a doubt that whether have you incorporated this into some systems like the managers there, and have you given these systems for implementation, or it's just an academic work?
Uh, it it was a part of a project that was in association with Airport Authority of India and Honeywell Systems. Initially, when we are designing it, it started as an academic research, but then we realized that to understand these operational complexities, we need to understand how on ground and how it happens on ground, and we actively collaborated with personals or the assistant general manager of Chennai ATC at that point of time. I think he shifted to Coimbatore air traffic management team, and he is an active part and a co-author of these papers. So we have shaped these models with his feedback so that it is as close to implementation reality and not just in academic research. And we have handed over the models to him, and we really wanted the Airport Authority of India to adopt, but I think there's a break in the pathways that we have still to achieve real implementation. Yeah, but I would definitely, as a researcher, I would definitely like to see if the Airport Authority of India can work with these solutions.
Okay, good.
Any more questions, please? Yeah, let me know.
It's me again. I was just wondering whether adding another runway would
Yeah.
actually optimize the whole picture. So, have you done something of that sort to, like, in the future scenario, how it should the airport should expand in the future or something of that sort? Have you considered?
So we have taken cases where we have compared the operational efficiency of one runway versus two runways. And of course, adding another runway does lead to beautiful results. And when I say beautiful results, I mean minimal delay. But we also found out that it might not always be required. If I can just manage things at a single runway level, as long as we are adhering to the capacity of that airport. So I think one runway should be fine. In terms of, I think the other aspect of your question is if the models can be used to predict whether should we add a new runway, if I'm not wrong. Is it correct?
Oh, yes.
Yes. No. So the decision making of should I add another runway or not, and is not being considered within a scope of my PhD, because it will require the consideration of other aspects of you have to do a cost benefit analysis. So there's not just an operational aspect. There's of course the geometry aspect, the environment aspect, and some other components that will be in the decision making. The runway addition of a new runway in itself is a very interesting problem altogether, and I think it will require a collaboration between payment engineering and economists and transport systems engineering and network science. So no, I have not explored that as a part of my PhD.
We also looked into the maintenance of these aircrafts or the runway of such scheduling activities also need to be considered, right? For
Yes,
the
yes.
airport operation. So
Yeah.
have you also done that?
Not directly. I mean, I'm not considered the maintenance schedule directly. It is an implicit assumption in the model, in a way that the maintenance might change the expected time of arrival and departure, right? And because of the rolling window nature, and because I'm updating the expected time of arrival and departure in the rolling window, if there's a maintenance schedule involved and that affects the expected time of arrival and departure, the model will consider it. But the model in itself do not answer whether a maintenance has to be scheduled or not. What happens in most cases are these maintenance schedules mostly periodical or these are almost fixed, and the airlines and the airport work around these schedules, and they kind of fix their ETA and ETD accordingly. Because let's say I think Hyderabad airport have maintenance somewhere between 12:30 or 1:30. I'm not sure if that's the right time, but yeah, they have maintenance somewhere in the afternoon or evening. So you will not find any flights at that point of time. No, this model will not be helpful in scheduling maintenance, but it can incorporate the effect of having a maintenance schedule into the results.
Okay, thank you.
Thank you.
Sir, while you model this system for this arrival and departure, have you considered the category of the aircraft, or does the
Yes.
fact?
Yes, and that's a very interesting consideration as well. So remember when I talked about the minimum separation between the arrivals and departures, right? That minimum separation I told is a function of the type of aircraft. So what we did is that when the model, let's say when I'm drawing the input for the model and solving the model, I also have to check which type of aircraft that is, and I have to check for the follower aircraft as well, and then I have to see what is the minimum safety separation for those two pairs of leader-follower pair. You can do it in that way. There's also another way of incorporating safety separation is if we can take the schedule and take the safety separation matrix, and both of them combining together can be adjusted as well. So it's a simple data structure problem, but it has to be taken care of. It is very, very important to take care of the type of aircraft and what will be the effect on the safety separation both during arrivals and departures.
So, sir, if that is the case, then the validity of the model across the different airports,
Yes.
that would be question, right? How we validate this?
Sorry, can you repeat the question? Sorry.
Sir, the model will depends on the category of aircraft.
Yes.
So you had considered the model in such a way that the model has been developed by considering mixed aircraft size and all, right? So will that be okay for the validation point of view also?
Absolutely, because you just have to take the input. The input data will reflect what kind of aircraft that is. So the model, the equations that are there already takes care of that. So even if your combination, you might have 500 wide body, let's say 50 wide body and 30 medium body and 10 small body aircraft at a given airport. The equation just see which type of aircraft it is. It is not specifically customized for a given airport. So even if you just shift from Chennai airspace to Mumbai airspace, it should automatically take care of the safety separation, of depending upon the type of traffic in that airport. It is quite customizable.
Okay, thank you.
Thank you.
Praveen.
Hi.
This is interesting talk. I'd like to know whether the factor of weather has been taken into account.
Yes, I have not taken it directly, and I think that remains a major limitation. And I've mentioned that in all of my papers and in the thesis as well. The effect of weather, yeah, there is no direct consideration of the effect of weather, and I should have taken care of it, actually. Uh, uh, yeah, I have one possible assumption. I think I answered to Anisha in the same way, is that implicitly it can be taken care of because of the setup that I have used. Again, because it's a rolling window setup and you have the time variables as stochastic parameters, as uncertain parameters. So if there is any effect of the weather on these, on the time or on the path complexity, or any change in the expected time, the rolling window should take care of. That's, I would say, I know it feels like I'm trying to cater to a lot of limitations through one sword. Uh, Maybe it's right, maybe it's wrong, but yeah, the rolling window does implicitly take care of if there are any changes. But yeah, I'm currently thinking about how to extend these models to incorporate weather explicitly, and get the solutions. And that's a very important aspect, and especially given airports like Mumbai, Chennai, and Delhi, they can have very frequent weather interruptions. Even Bangalore as well, sometimes have very severe weather interruptions. So uh, there should be some explicit consideration of the weather in the model.
Okay, thank you.
Any other questions from the participants?
Thank you, sir. Now I request Sri Ashike Asad, Junior Scientist, Highway Engineering Division, NATPAC, to propose the vote of thanks.
Thank you. Thank you, Dr. Aitichya Chandra, for delivering in such an engaging talk on modeling an efficient system for airport arrivals and departures. We truly appreciate the time and effort you put into preparing and delivering such an engaging talk. Especially the inclusion of case studies of Chennai Airport and also the interactive discussions with the participants has also enriched our learning experience and provided us with valuable insights. A special thanks to our director, Professor Dr. K.P. Sudhir, for his constant guidance and support for shaping this event in a wonderful way. I'd also like to sincerely thank all the participants for their active engagement throughout the session. And also a big thank to the entire NATPAC team for their efforts in planning and organizing the session so smoothly. Once again, thank you all for joining this technical talk, and we look forward to hosting much more enlightening sessions in the future. Thank you and have a wonderful day.
Thank you.